So now we move to the main topics of our course, which is the classical mechanics. Both of the previous chapters is mostly about the introduction before the classical mechanics, which is the main topics. So now we're gonna get insights to this topic. So let's see how interesting of this classical mechanics from that day and still relevant until this day. So what is the mechanics? And the mechanics can separate into two big parts. The first one is called kinematics. Kinematics is what happened, and we try to explain it in terms of the motion of the object. In this case, like you can see this bird moving by some force, right? And it's moving like projectile further. So this is how it's moving. So in kinematics, it can explain how this part happened in terms of the projectile. You can explain about the displacement of this motion, the velocity of it, the acceleration, also with the time. So all this, what is happened, is can be explained. So you can use kinematics to explain it. But what mechanism behind? That's the reason of this motion happen. We can use what is called the dynamics. The dynamic is the force, is the influence of this motion. So it's combined with the force, in the momentums, energy, work, and also the power. So not only this, but also a lot of things that can happen and influence to the motion. So what you can see here, the motion of the objects in classical mechanics can happen in not only 3 dimensions. You can set this like a 2D plane, which is happen in a 3D world, or it can be happen in one direction. Not the English boy band, but not British boy band, but this is like the direction that you can see this football moving, and you can see the velocity, displacement, and maybe some acceleration due to the force that happened. So it happen in 1 dimension, 2 dimension, and also 3 dimension. But first of all, we start with motion in 1 dimension first. You can start from the beginning, and now you apply to 3 dimension. What is happening in real is happening in 3 dimension. To identify the properties of the classical mechanics, you already know the properties of the vector as the scalar quantities and the vector quantities. So now what is happening here, we're going to explain in terms of vectors only. But as you can see, if you said all the property here is vector, but if it's happened in 1 direction, you can use plus and minus sign to represent the direction. If it's in forward direction, you can set it's in plus sign. If it's go backward direction, you can set it's in minus sign direction. So rather than you use the unit vector I, j, k, now you use only plus and minus sign because it happened in only one components of the vector. It may be only in I plane, only j plane, or only k plane. Let's start from this. The first one, how about the position and the displacement? So if you have the initial point or the reference position, you call this position as a zeros. So if it's go further away from 0, you can say, okay, this is the displacement plus, for example, here is 30 meter from 0 to A. But if you gonna state about the position or displacement that the car moving backward, for example, like this, from 0, you can see the car moving backward for minus 40 from A to E. If you state E is 40 here, right? And this is what called the displacement. If you state from the initial point, this is the initial position, to the final position, or to the final position. It depends on how this object moving. So now let's see what can be explained with this. So what I can show you, if you approximate the distance and displacement is going to be different, because distance, as you remember from the box moving, the distance is combine the total part, like all the way that the animal or the ants or insect moving along this part. This is called distance, right? But displacement is count only the first point to the final point. It is displacement. So now if you're gonna state about the displacement of this car when moving from initial point to A, B, C, D, E, and F. So the distance is the summation of the distance, right? Summation of the distance from 0 to A is 30, right here 30, and from A to B, as you can see, if B is around here, so it's plus 20. And now from B back to C, you can see it's backward, but you sum it up 10 here. This is the distance from B to C. And how about the distance from C to D? It's go backward for 40. And now this is go another 40 to E, and finally to F. I said is 60. So here is the distance. You sum up all the distance. So this 100, 150, and 200 in meter unit. Right? It's like you're moving from point A, B, C, D, E, F. You sum it all. And what happened about the displacement? If you think about displacement from A to F, and this is also from A to F. So you just point out only when the object moving forward and backward. So this is from A to F, sorry, no, not count 30 yet, because 30 is from zeros, right? You start from A here and going to F. So start with this 20 and backward 10, backward 40, backward 40, and another 20. So I'm sorry for 30 initially, because it's not start from 0, start from A to F. And how about from A to F in terms of displacement? You see A position is at 30, and how about F is at 60. So your displacement is here, the initial point to final point, like this. I will use write out as linear as possible from this point to the end point. So what you can write down is delta x, right? So which is this is plus 30. You have delta x is the final point minus with the initial point in terms of vectors. So what is your final point is minus 60, and what your initial point is plus 30. But what you have to do, you have to subtract them off. So subtract with minus 30. So what you're gonna get, your displacement totally is minus 90 meter. So minus is your sign to state of backward. This is about the direction, and the magnitude is 90. This is your displacement. You can see the difference between a distance and a displacement, which is distance you combine all of the distance, but displacement you count only the initial position and the final position, which is the xf minus x1 for your displacement. And how about the speed? The speed is what you have distance divided by time that is taken. So you can see this motion is moving in 50 seconds. So your distance is 200 over 50. So you got the speed as 4 meters per second. So the dimension of the speed is L over is M over L, right? As we did in our first chapter, is L over T, my mistake, L over T. So the unit is meter per second. But how about the average velocity? It's the displacement over the time. So you got minus 90 over 50 is minus 9 over 5 meter per second. So what you can see here, the speed gonna tell only about the magnitude, because speed quantified from the distance that have no direction is only magnitude that happen and complete, because the distance and speed are scalar, right? But the displacement and velocity is are vectors. So the average velocity come with the direction, which is they go backward in terms of direction with this 9 over 5 magnitude in meter per sec unit. So this is the difference between distance, displacement, speed, and average velocity, right? So now what you state here is you compare to the frame of reference. Frame of reference is what I state initially as your 0 position here. 0 is your frame of reference. You reference everything you relative to the 0 position. This is your frame of reference. You will learn more about all these definitions through the calculation of these chapters. How about the first example? So what you see, this runner moving from point A to point B and point B to point C with different velocity, different distance or displacement in this case. So you like to determine the final average velocity here. Average velocity here. How can you determine it? If you like to determine the average velocity, how can you find it? You're supposed to have the displacement over the total time, right? And do you know the displacement from A to C? Because the average you want to find from A to C. Okay, from A to B, what is that? It's about 100 meter. And how about the B to C is 200 meter. So now you got the displacement from A to C already, right? It's 300 meter. If you would like to write down in terms of the vector, you can give direction to it, right? Because the plus x, you can use I in terms of the unit vector. You can write down as I here. Or you can ignore it because you know it's moving in one direction. It depends. Show it as magnitude. You can write the displacement like this. But what I'm suggest you to write down should write down like this, because in the next chapter you not only learn about one direction, but you can do more 2 or 3 direction in 3-dimensional system. So now you already know the displacement already. I write down as a vector for you because the velocity is a vector. To remind you, it's not about the scalar and vector now. Most of quantity you calculate in vector, but you ignore the sake of vector because you know it come with the component in same direction or in same unit vector. Whether it's going forward or backward, it depends on the size plus or minus in front of that magnitude. So now another task is to find the total time. How can you find the time from the velocity and distance. So you know, when this moving at this displacement from the first period is moving with 8 meter per second, and from the second period from B to C is moving with 5 meter per second. Yeah, if you would like to find the time from each part, like A to B, from B to C, as you already know from the constant velocity, S equal to Vt, right? So that you can find T from S over V. As this case, you know the distance or displacement in this case, we overlap distance and displacement here because it's in dimension, but most of the value that you observe here, mostly they are displacement, right? I'll use a displacement to ambiguous of all this information is going to be more precise rather than using the distance. So now we know the displacement from A to B is 100, and how about the velocity? 8 meter. And how about B to C? Is the displacement is 200 over 5 meter. So now you're gonna find time of each one. So the first one is 12.5, and the second one is 40 seconds. So now this is your total time. T total is equal to 52.5 seconds. So now you can find the average velocity. V AVG is equal to total distance, which is 300, and you know it's in I direction, and divide by 52.5. So finally you're gonna get V equal to 5.71 meter per second, and you already have the direction for it. It's in I direction. You can write down only, if you would like to find only the magnitude, here is 5.71 meter per second. This is also correct for 1D motion. It's okay. But for further and for completeness, you can write down in terms of vector, because you know this velocity value is a vector quantity, not the scalar quantity. Before is the average velocity. You know the average velocity is the displacement over the time as a vector. But if you would like to find some instantaneous velocity, what instantaneous mean? It mean like you not average the whole motion. You just looking into one event and see what is this velocity is it. That is your instantaneous. When you combine to the average is the whole displacement that you're moving, and you average the displacement with the time. This is your average velocity. It's different. So this is how you divide it. Like from the average velocity, you have the displacement to focus. As you can see, from different part of it, the velocity may not be the same. So that when you average, it doesn't mean at this point B, point C, point D, or point E are having the same velocity compared to A to F. So you would like to investigate at one specific point, for example at B. What you do, you just close down the time space. So when you divide by dt, you would like to close it as small as is possible. And at that point is when you introduce the differentiation, or called diff, into the term. So if you would like to find the instantaneous, we just diff position or displacement with the time. The change of the position, the change of the displacement is your velocity. So thing is, if you would like to average, find the displacement over the time. But if you would like to find the instantaneous velocity, find the function of x that relate to t, and you dip xt by t, that you're gonna get the instantaneous velocity. So we will understand more through the experiment and example. So it's the part of the experiment that you try to time on the runner, or this example is the result that you find the way that this runner walk or run according to this equation. So this function represents how this guy moving through the displacement. So xt is x as a function of time. So you can say it's changed with the time in terms of polynomial like this. And this guy running in forward direction. So if you like to determine the average velocity from 1 to 3 seconds, so this is the point 1 second to 3 seconds. So what you would like to find, you have to find the displacement and divide by time, right? Which is the displacement is the different. You can see the delta is different of x from position 2 to position 1 and divide by time. So your job is to find the position 2 and position 1, which is position 2 is x at 3 equal to 3 at 3 seconds, and x1 is x at 3 equal to 1 because it's 1 second. So by this you can find the x3 and x1. So I will rewrite this again. So it's quite big and fill all the space. So VAG is equal to delta x and t, and delta x is x3 minus x1 divided by t. So your x3 now is minus 4 and sub 3 to 3, and then you got plus 2 3 square. So that your x3 is, sorry for my pronunciation, I'll do it correctly. I will write down the final answer is 6 meter. And how about the x1? x1 is you sub 1 into the t, so that this is minus 4 1 plus 2 1 square. So the final answer is minus 2 meters. So you got the displacement at t equal to 3 is 6 meter, and for t equal to 1 it's minus 2 meter. So now you're gonna get your final V average equal to 6 minus 2 over the time period, which is 3 minus 1, 3 minus 1. So here you got 8 over 2. So your final V average is plus 4 in I direction in unit of meter per second. So here you got the direction, vector, and the magnitude. This is your V average. But if you would like to determine the instantaneous velocity at this time point, how can you find it? The way to find V instantaneous is you differentiate the function of the position or displacement with the time. So now you dip x over t is you dip this equation minus 4t plus 2t over 2, right? And then what you differentiate, you just need to rearrange this and diff all the term inside. So now you get, I will write this slowly for you initially, and after that I will do quickly. So this is what you get after that information, and you dip it immediately. So the way to differentiate it, if you have the power, you have to -1 and you get that outside. So in this case you get the -4 out of the first differentiation, and the second one is 4t for the differentiation. This is your Vt in meter per second. So this is how you find the instantaneous velocity, right? Just differentiate it out, the function inside. And what the question asking you about is V at t equal to 2.5. So now you sub them in, so it's -4 plus 4 multiplied by 2.5, so that you're gonna get the final one is 6 meter per second. If you state it as the vector, which is velocity is vector at t equal to 2.5, it's gonna point to I direction plus I direction here. Right, now you can see the differentiation between the average velocity to the instantaneous velocity. So now it's your choice, and what question asking you about, you should use the proper definition for the different